Hi, everybody. My name is Dennis Doherty. I'm a professor of chemistry here and also chair of the Division of Chemistry and Chemical Engineering, which is Scott's home. It's a pleasure to introduce Scott Cushing tonight. You came to hear from him, so I'm going to keep this very short. Scott is a native of West Virginia, born and raised, got both his bachelor's and his PhD at the University of West Virginia. Then we finally got him to move to California, first to Berkeley, where he did a postdoc, and then came down to Caltech as an assistant professor. In just a short amount of time, he's only been here 4 years, Scott has built a really exciting and vibrant research program. Scott is in our division what we would call chemical physics group, at using physical and spectroscopic tools to probe chemical systems. Scott does both experiment and theory, which is a real plus in this field nowadays. And as you'll learn, he's at that area involving quantum sensing, quantum measurement, and quantum computing that is such a big topic of interest on our campus today. Another thing that has been remarkable about Scott in his short time here is he's taken a real leadership role in diversity, equity, and inclusion and outreach on the campus. He has been an absolute leader in our division and on the campus, developing programs, including a peer-to-peer mentoring program at Charles Drew University, the only HBCU in the state of California. And so we're really proud and grateful that Scott did that. In a short time here, he's been named a Cottrell Scholar. He's a member of the prestigious National Academy of Sciences Committee on the Interface of Chemistry and Quantum Information. He's won the KNI Wheatley Award, as you might know. So without further ado, I'll let Scott tell you about his science. But before he gets started, we're going to have a short video to introduce the program.
I'm originally from Charleston, West Virginia. I grew up basically fixing cars and being a home mechanic and doing yard work, basically anything that, to make a little bit of money on the side. But I always loved building mechanical things, and my grandmother and my parents, anytime something broke, they gave it to me. So I love fixing things like that. Going into college, I kind of didn't know what I was going to do. I had some thoughts that I was going to be like a mechanical engineer. And I was in a physics laboratory and they showed me a laser and I was like, shut down everything. That is going to be my career. I love the lasers. Honestly, it still gives me the same joy, like sitting there cranking bolts on my vacuum chamber as it did back in the day of, exploring how to do a car engine swap. My name is Scott Cushing. I'm an assistant professor at Caltech in the CCE division, which is chemistry and chemical engineering. I'm in chemistry because I'm what's called a physical chemist, the balance between a chemist and a physicist. The Noyes building has hosted a huge amount of instrumentation builders. Everyone from Jack Beecham with type of mass spec, Albert Zawell, who's one of the fathers of ultrafast spectroscopy. General building donations, if you read the placard, comes from the person who invented Xerox. Caltech chemistry department has a rich kind of legacy of building instrumentation. They don't care how quickly you produce science, they just want you to make good science. And when you do instrumentation building, you really need that support because it takes me 3 years plus to build a new scientific instrument. Some of us are blessed with a theoretical brain and you can just go and look straight in an equation. But for me, I needed those mechanical stepping stones to build this instrument, build this instrument, build this one, to really build up that broad view of quantum mechanics that you need. There's two kind of sides to these entangled experiments, doing classical things better and then finding new phenomena. So, if let's say we just have an atom or a molecule and, it absorbs a photon, it takes that energy into it. What we're looking at is how we can combine multiple of these absorptions and do what we call entangling them. And once we entangle them, we can then use them for things like new forms of sensing, quantum computing. So many of these things are enabled by my colleagues in collaboration at Caltech. Alireza Morandes helped me learn how to do the sources. Betty Hong is helping us do what we call neuroimaging. What's so unique about photons is that when they interact with what I call matter, anything, you're sure when they interact with a science experiment, anything you could think of, you actually can get a very precise view of what's going on in the quantum mechanical world, which, is full of its own subtleties that you can't usually see. The quantum part, the entanglement, basically does away with all the classical light ideas. It's more of a discovery-oriented field. The students, they'll have to rebuild setups once a week, once a month. Every time we build it, we just learn a little more and you just keep pursuing that. we can discriminate individual molecules from a huge bath. We can see how that relates to huge macroscopic picture, but the hope is we can take that one step further. Your watch, for example, watches your oxygen by just looking at some absorption, right? That's what we call linear sensing. But what if instead that same watch is actually measuring, say, the chemical reaction rate or the protein folding of some specific medical task that you're trying to understand? So that's the type of techniques that we're trying to use these entangled photons to unlock for the average person. But you also have to wonder, okay, what's going to be that next big science? And so that's one of the things we do, and that's why we're exploring these entangled interactions, say, between multiple molecules. As we get more and more degrees of this quantum weirdness, let's just say, you're going to have new physical phenomena pop up. There's always going to be some crack. Is it the experiment that's wrong, or is it the theory that's wrong? And that kind of process slowly gets you there. So, yeah, I don't know exactly where it's going to be, but I know that quantum will continue to rule all the devices, everything you use in this world. But surely, the next science is also going to come out of it.
Good evening, everyone. So thank you so much for taking the time to come out here. I appreciate all of you wearing your mask. As a speaker, I'm allowed to remove mine, so I am going to do that. But I appreciate you all following our masking guidelines. Before I get started here, I do, of course, want to thank the Wheatleys who are here for sponsoring this award, from which I'm doing. There's actually a really fun connection here, and Alareza, who was last year's K&I Wheatley Scholar and is here, based on his video, we kind of started collaborating. I watched it, and I finally got a grasp of all the amazing things he's doing, and I was like, whoa, dude, we should totally do this together. And we were just walking back from lunch, and after lunch, we already spent 10 minutes talking again. So it's great, this continuity that comes around from your all's gift. I also want to thank the Kavli Foundation and the Kavli Nanoscience Institute, from which most of this work is done and which is here on campus. Also, very quickly before we get started, it's tradition within the chemistry and chemical engineering department that we have a DEI moment, a diversity moment, before we actually give any big presentation. And the idea of this is just so that we can kind of normalize or make community about things that are very prominent in academia, but which we don't always talk about. And for me, it's a very easy one to come to. And for me, that's mental health. Mental health issues I think it's 1/3 of graduate students report, but in reality, the estimates are closer to 80 to 90% of scientists at some point in their life go through a hard mental time. And I just want to stay up here to say, that I also went through that. I don't want you to think that I'm up here, this has all come from confidence and poise. Rather, this has come through, a lot of time. I went through some hard mental health issues, but after 5 years, I think, 6 years of therapy and psychiatry, this is the first talk I've ever been able to get up here and actually be excited for, instead of just putting on a face because I'm so nervous inside. And so I want to encourage you all, thank you. So I just wanted to encourage everyone, real quick, scientists, parents of scientists, high schoolers, anyone who's here, anyone who's listening, listen to your head and don't be afraid when you have these types of things. Never let someone tell you, just feel better, just be happier. Never let your mind tell you that. Never, how can I say it? Imposter syndrome, everyone has. Never think that just someone, because they look poised, they look composed, that they're in some way better than you. We all have these thoughts in our head. You can ask every scientist here, even the Nobel Prize winners. You go up to them and say, okay, oh, you must have control of your world. And even they'll admit, they're like, no, I sometimes don't feel like I'm doing enough. Am I actually contributing? So I want to have you those things in your head, and never be afraid to give therapy a try. One cost, especially here at Caltech, it's free. Go for a session, why not? At most, you waste 30 minutes of your time and you go on happy in your life. So I just wanted to give us that moment real quick. Before I transition into something that's much less tangible, even though I think you could say mental health is unintangible, but let's talk about quantum mechanics. And I hope at the end of this talk, you come away from it with a few different things. One is I'm going to use analogies to cars and toilet papers too much. I hope you think of me when you think of cars and quantum mechanics. I hope you don't think of me when you think of toilet paper. But it's a useful analogy. So with that, though, I kind of want to dive in because our lab is doing a very discovery-oriented type of science. And this kind of science comes around, like we said, with instrumentation building. So I want to start at the origin here, right? Maybe this brings back memories for you. Maybe it doesn't. It definitely brings back memories for me. The classic car mat. And I can kind of describe what I do in terms of this mat. You know, I'm a spectroscopist, which basically just means, again, I'm someone who builds instruments to measure new scientific phenomena, whether it's very, very erudite things like the basis of quantum mechanics, or it's very practical things like an X-ray. So whenever you think of any device, you know, whether it's, you know, yourself, whether it's your cell phone, like I said, toilet paper, all these things rely on quantum mechanics. Basically, everything around you is quantum mechanics. It just all kind of gets averaged out. But I want you to get out of that averaged out point of view for this presentation. I instead want you to sit, and I want you to think about, okay, if we have some device, it's going to be some complex network of what we call electrons, a fundamental quantum particle. These electrons are between atoms, and you keep building up. You get pathways in a cell. You get all the wires in your computer. The job of a spectroscopist is to look at this device and not just take the output, but to figure out everything that goes on in between. So in this talk, this is what I'm going to be talking about, what we call photons and electrons. Photons are what we call the quantum particle of light, and I'll explain that a little bit more. But the idea here is that, you know, whenever light interacts with something, whether it's your shirt, whether it's your, well, I don't want to say toilet paper again, whether it's any of these things, light is always a quantum mechanical interaction, which is really interesting if you think about it, because it's our most basic and some would say, you know, most important sense, but it's all quantum mechanical. And so a great way to start to understand these complex networks is to use photons. And that's why I love lasers. That's what I do with lasers, and I do what's called ultra-fast science. So this is me. I'm the small child. If you think about it, the parents who are around here making sure I don't touch and break anything are my grad students. It all works out. But here's what kind of a spectroscopy setup looks like. As you can imagine, it's not necessarily a simple task. This right here is one of our largest builds. This creates transient X-rays, and I don't expect you to digest it. Just look at it and see it's a mess of wires, mirrors, plumbing, vacuum chambers, pretty much any type of skill you could think of, computer writing, automation. It all goes into actually building these spectrometers. However, one of the reasons I'm interested in entanglement, and a theme we're going to slowly get through, is that entangled photons can actually take systems like this and shrink them all the way down to what we call on-chip. Things that could fit in your thumb, things that could fit inside your cell phone. So that's the real potential and why I want to focus on that. So again, you know, I just want to give the idea, you know, spectroscopy is basically everything. You know, people ask me, you know, oh, what types of instruments do you build? Actually, one time I have to admit, I told someone I was an instrumentation maker on a date, and she asked me if I made violins. And I was like, man, I wish I was that cool. But whatever. Instead, I play with lasers. But everything you see, it's easy to think of healthcare, X-rays, CAT scans, NMRs, MRIs, your watch. These all use photons. Now, we usually only think of light as being visible, but light spans this huge range from radio waves to X-rays and beyond. But I want to come back to this point. Without quantum mechanics, your eye would not work. The basic molecules in your eye are actually incredibly complex quantum mechanical systems. So when you come out of this, I want you to think, I mean, I don't want you to think about, you know, entangling the world, but always remember, you know, the world around you, you know, sometimes people say quantum mechanics feels so intangible. But all the basic interactions, even down to your eyeball, all rely on this. So what I want to focus here on is, you know, what we're going to do in order to start to kind of understand and have some of these quantum abilities is I want to take us away from what looks like a blank image. I made it blank on purpose. You see, this is white, right? It's white light, it's going in your eyes. But in reality, if you've ever listened to Pink Floyd, you've ever seen a rainbow, you realize that white is made of multiple colors. So what we're doing in my work is we're basically taking just a single photon, a single wave, and using that for spectroscopy. Whereas in my other work, when I say classical light, it's like we just have this white screen going in. And when we do this, you know, if we have just a ton of quantum mechanical things, they average out. But once we start to just pick one, that's when you're going to start to see some very interesting and cool new science come out. So to kind of give you another analogy of this and give you a little bit of understanding, because I have to use some jargon in my talk, I want to bring up the first tiniest bit of an instrument here. This right here is a standard setup for how we make entangled photons. And the idea is that we're taking one, say, blue beam, one photon, and we're splitting it into two. Blue goes into two red. It's because of energy and momentum conservation. I know it's a little weird to think about of light changing and equaling each other, but remember, it's a particle in a sense. But what comes out of it is these beautiful types of rings. And these rings are actually wonderful. Poor Michael and Paul, this image has probably been used 1,000 times in every single talk on entanglement ever given, but it's just so pretty to look at. But there's actually quite a lot of information within this. For example, I was talking about classical light. Remember, this is the white square on the screen. This right here is basically, let's say we take these rings. These rings are being created because we're splitting a photon, but we just added them all up together again, right? Red, green, blue. That's what's in your display, your computer, everything that allows you to basically see color, all these technologies, you mix red, green, and blue. So this right here is just a sum, like I said. The quantumness kind of goes out. We could do something else though, and we could say, okay, well, what if we made indistinguishable photons? Let's say we only have blue of this one color, of this one frequency, and we have multiple of them. Well, we have no idea which photon's actually which. And when you do that, you do start to get a lot of quantum weirdness. However, we want to take things one step further, because I told you what we're doing here is splitting one photon into two. So if we go to these points where these rings of color overlap, within there, you can't say which photon is which photon is number one, which is number two. And this is what we describe as an entangled state. I'm going to get more into it, but the weirdness here is, you can't just say, okay, it's in photons, or you can't say it's photons of a lot of different colors. It exists in this quasi, I don't know, effervescent type state almost, it's just a state where we have two photons, we have no idea which photon is which or what which photon is doing. But I can make them that much better analogy. Like I said, we got to get into cars some. So let's think about a four-way intersection. And let's ignore for a second these aren't LA drivers. If we have these cars coming into a four-way intersection, there's four possibilities, right? Both cars could leave through A, both cars could leave through B. It's a 50-50 statistical probability. If these things were ideal cars, we can say, if no one had any directions. This right here is an optical element, we call it beam splitter. Now we can take this one step further and we say, okay, what about those indistinguishable photons? We can think of this as now we're towing two cars. They only have two possibilities, right? They both either have to leave A, or they both either have to leave B. So we still have 50-50, but we've taken apart their ability to break. Now here's where things are weird. If we had entangled cars, we don't know whether the car is in A or B. They could both be coming through this way, they could both be this way, one could be here, one could be here, until they interact and those two photons that we took apart combine back together and have more single photon-like properties of the photon they came from. We don't know the interaction. So it's still 50-50, it's the same statistics, but we have no idea where the car actually is. We just can measure on the output, okay, a car came through. And this is where some of the spectroscopy and the interesting stuff comes through. So two other ways that I can kind of demonstrate this, and this is two fields I just want to briefly mention that I myself don't work in, but I think that I want to bring up. They're very interesting, they're relevant to my work even though I do different. And let's now take an analogy, okay, we now have just a left-right turn. And let's say we had two different color cars, but they're entangled. Now instead, unless we have someone at B or someone at A, until those cars arrive, we have no idea which car is which. If we have someone say at B and they say it's blue, this is kind of where the debate and the spookiness and all the things come up. Well, instantly they know it's A. But to be clear, you aren't breaking any laws of causality. You can't break the speed of light. I mean, one car could be on the East Coast, one could be on the West Coast, one could be here, one could be Mars. But you still have to communicate in order to actually transfer information. So you aren't breaking any laws of physics, but it's a very interesting thing because you're going from we don't know which car is which to instantaneously when I measure it, I know exactly where the cars are. So this right here is kind of some of the science between quantum information science and quantum cryptography. These are not my fields. I encourage you to look at the Caltech Science Exchange with the Institute of Quantum Information and Matter, IQIM, where there's lots of great public talks. But the general idea you could think is if you start building up very complex patterns of these, you can not only communicate information, but you can make very complex codes, right? Codes that if only one person can understand and the other person. Now, we can also make another analogy to another popular field. Again, this is not my expertise. I really encourage you to look up these other resources because it's fascinating topics. But let's say that now we had a ton of cars and they were all entangled. We had a traffic jam of entanglement. But because they're entangled cars, we have no idea where the car is, which one is which. They all just exist at the same time without being individual. Well, if we did some operation, let's say we had a rear ender. Let's say we had a rear ender here with a blue car. This will collapse. In other words, simultaneously all these operators will go and we'll see a blue car come out. Now, if this was a classical computer, it would have to count each car and then it'd have to find, okay, this is say car B1. that's the one we hit. But the thing with this kind of instantaneous there but not there state is your calculation happens all at once. Now, it's a very bad analogy. My colleagues would correct me, but hopefully at least gives you a little bit of idea of why people are interested in this. But let's get back to what I do, because I'm not in these fields of quantum information science or computing. Remember, I measure things. I'm trying to take that roadmap and dissect it. So why is entanglement important there? Because I told you all light is quantum mechanical. Why do we need entangled light? Well, let's think of another little experiment here. Now, instead of just saying it goes A or B, let's say we have continuous traffic and we measure the probability of the cars leaving through both sides of the intersection. Again, if these were ideal cars, it would be 50-50. However, the entangled cars are different, right? Because I told you, unless they intersect, they don't kind of form back into their original cars. We don't know where the cars are, it's only when they interact. So if we looked at it as a function of time, we would see that, okay, if we count A, if it's coming out A and it's coming out B, we would see that, okay, when the entangled cars come at the same time to our intersection, they only leave A, they only leave B. So if we looked at the cross correlation of A and B, it would go to 0. This right here gives us a temporal resolution. So the key, if I wanted to understand any system, is I already told you we have frequency. That's the photon, that's the color of light, that's energy. But in addition to that, we also need temporal resolution. So we can not only measure different systems, but we can measure how they evolve in time. So this is kind of the basis for entangled spectroscopy. And in order to do this, the experiment actually looks very much like the stop sign I was just showing you. Here's my most basic schematic. We'll keep getting a little bit more complicated. Remember, I take my laser here, we create our entangled photons. I can put in some mirrors, you saw the very complex setup, we manipulate everything. But very simply, we put in a time delay, then we put them on what is the equivalent of a four-way intersection, what we call a 50-50 beam splitter. And then we count what's going on in each one of these. So what's going to happen is we can have two different types of spectroscopy I'm going to describe. One which is large in the field is linear interactions. The other is the one that we focus on, which is nonlinear interactions. And the way you can think of this is, okay, we have our stop sign. Remember, I told you these cars, they're in this weird kind of mixed state. We don't know what's what. But if you have one car crash, well, you're obviously going to know which car you had, right? It's like you measured it. If we have when they cross, though, you're now going to have, okay, with both entangled things interact with the object, does that object support entanglement, the dynamics that come out? So in my lab, and I'll show data later, we're just kind of looking for modulations of this dip which tell us about how our system's evolving. So let's start with the first one, what I would call linear entangled photon spectroscopy. And the most interesting thing about this is that because of this entangled state, and because of that idea I told you, where if we measure at B, we know what's at A, you can do some interesting variations, you could say, of classical measurements. Because the idea here is, okay, I have my entangled cars, now I have my car crash. I couldn't find a good kabam, but whatever. We have a crash. And then when we have this crash, we now know what's going on at the other side, right? If this was a crash with blue, we know this is going to be A, even though the car A never interacted with this side of our stop line. So when we do this in an actual spectroscopy experiment, this allows us to have some very interesting concepts. One of them, and this was a great paper shown here, is that I can have two different colors of light. This one was visible and IR. And let's say the IR, you could think of heat around you, it measures, it's absorbed by water. In this case, it was CO2 it was looking at for the absorption of light. But the thing is, we have the interaction with one arm of the entangled photon pair, but we can measure it just using the visible. So this right here is kind of a narrow case. You can think, okay, visible IR, that's not big of a difference. It's great, we can do spectrum, but in reality, we already have IR light. Why do we need this? Well, maybe a more interesting case to think about, and this has been done, and it's a very rapidly growing area, is you can actually do this with an X-ray and a visible light photon. So that means that there is a possible way, it's still way too weak, still very early in development, that you could basically do an X-ray measurement and then measure it just using a regular camera, instead of having to have specialized X-ray apparatus. So let's take this one step further, and we can kind of carry that idea, and you can see the usefulness of these techniques. Because now I'm going to make things, well, a little bit simpler, a little bit fancier diagram, thanks to Miles, who really has innovated a lot of this field. But instead of just measuring the light, the colors, let's measure an actual pattern. Let's measure an image in one arm. So let's say in one arm of this, I put in a picture of a cat. Because scientists aren't creative, and whenever we talk about science, the only thing we ever talk about is cats. It's cliche, we have to find a new animal one day. But we put a cat in one arm of this, and then in the other arm we record an image. Well, the same thing's going to happen. We can actually measure this image using photons that never are on the target itself, the image itself. So why this is so interesting is let's go back and think about the X-ray case. This means theoretically we can make an X-ray image of your body and then measure it purely using visible light photons. So this is very exciting, because it allows you to access ranges that aren't normally possible. I mean, if you could do it, it's not going to be safe to continuously irradiate yourself with X-rays, but you can imagine how this can lead to field portable and other interesting technologies. Another cool thing about this is that, I told you that, okay, a classical state is a bunch of quantum photons combined. Our entangled state is this weird mixed state. But we can actually differentiate these quite well. So in these images, it's the same type of idea, but now we have a classical light pattern shown on top of the underlying thing we want to image. So we're irradiating our entangled source with what you could think of as a jamming laser or visible light, and we're able to retrieve from underneath what, with our eyes, is a hard thing to see, an accurate picture of what lies underneath. This is a very interesting thing. This picture, again, is from Miles Paget, who's really one of the innovators here. But Ben Sussman's another person working in this field, and he's shown, I think, 1,000-to-1 rejection of classical light. So you can imagine as we move towards self-driving cars and things like that, you need to be able to reject things in order for their operation. So this is kind of a very interesting concept. But it's not my favorite thing. My favorite thing is the nonlinear aspect. And all nonlinear means is we're going to start having two photons interacting instead of just one photon interacting. And the reason why we do this is you can imagine if I just have one child and I tell them to simultaneously move all the cars on this map, it's quite difficult. In other words, it's kind of like, say you're sitting on the side of a highway and we have all these different cars going past you. All these different cars are moving, and I tell you, okay, from one position, constantly tell me where all the color cars are that passed and what the pattern is. It's near impossible. So this is what we refer to as things like linear spectroscopy. If we have a complex system, we have multiple molecules, say, together, or we have a solid, and you measure it, you just see kind of a bunch of bumps. There's no distinct signal for what's going on. So instead what we do is basically the equivalent of bringing in a bunch of your friends. And now your friends can help you count the cars. Once you do that, it's easy, okay, right? We assign one person to red, one to blue, one to yellow, etc., and they count, and it kind of organizes our information. So the idea of nonlinear spectroscopy is that instead of just measuring a single source of photons, we usually use multiple laser pulses. So we have multiple observers of the system, and by varying them with each other, we can gain more in-depth information and take just kind of those bumps and split it out into a multidimensional data set that actually can figure out what each system is doing. The hard part about this, though, is that nonlinear spectroscopy requires big lasers. Now, I'm exaggerating here. I just love this one because it's kind of my baby. This is the first instrument we built. But it takes a big pulse laser, which are expensive, and they're kind of complex. Now, they're getting much better. These days, IR fiber lasers and other type of lasers are very compact and portable. But if you really want to do what we call nonlinear spectroscopy, you're usually stuck with something that takes, I don't know, a couple PhD students to maintain, a lot of money, everything that goes with it. Now, the interesting thing, though, what we can do here is with entanglement, you can think we have, okay, here I have 4 observers. What if I entangle them so there's simultaneously one observer but not one observer? In other words, I can take my entangled people here and we can have this linear state interacting with a classical system, even though this right here is like one photon because they're all combined together, right? If we can't tell them apart, how do we know it's not the original photon they came from? So when we do this, we're actually able to take a classical system that's very convoluted, then we're going to be able to interact with our entangled state, and we're going to be able to get a nonlinear result from a linear photon. And this has a couple of important things. The first one is it allows us to really shrink things down. Because when we now are doing our nonlinear experiments we're developing in our lab, we're slowly moving towards basically the equivalent, of this laser pointer. Basically, a cheap thing, you could buy laser pointers. Oh, they were so fun, like back in the 90s and 2000s when I was a kid. Then they were probably like $30, but you can probably buy a laser pointer online. I mean, you can buy laser diodes for like 10 cents or less, because lasers are everywhere. So the idea here is basically, with entanglement, we're getting rid of this, and we're slowly simplifying it to this. This right here is about a 1 foot by 1 foot square. All the light goes through fiber optics instead of mirrors, so we don't have to align it. And we're slowly getting these systems smaller and smaller. The idea being we want to bring, like we said, we had such a rich history of instrumentation building lasers. Jeff Blake with his terahertz, Michio with his atmospheric measurements and frequency combs, Ahmed Zewail, who's one of the first people to kind of make nonlinear spectroscopy popular. But these things have always been limited to the lab. They're very, powerful, but they're just complex. So we're getting simpler. So what's a good case? Why is it a good case we want to do this? Well, I tell another collaboration I'll point out, someone who's helped me, in my career, is Betty Hong. And she basically does neural imaging. This is not her picture, this is just beautiful. But the idea is, with these scientists, and what Betty does, is they want to create 3D images of, say, the neurons in your brain. So in order to do this, you could think, okay, how can I get a 3D image? If light goes through, remember everything's jumbled up. You'd see all the things going through. If you hold up a black sheet of paper, you can't see light through it, right? So the idea is to say, okay, let's make a molecule here now, and when we have this molecule, we're going to make it such that it can only give off light when 2 photons interact with it. So this way, if we have lasers and we kind of shine them around and we put them in corners, wherever they intersect, we'll be able to get an image. And this allows you to bring up a 3D type of thing. Now, the issue here is how the laser intensity and the probability that goes into this comes into play. Because the idea is, okay, if I want 2 photons to interact with the same molecule, it's like I need a bunch of basically single rear enders, just 2 cars hitting each other. So the laser intensity we're going to need, the power we need, is going to go as the number of cars we have, the number of cars going on the highway, times the number of basically interactions we want, rear enders. So if we want to do 2 photon, it goes as the intensity squared. We're now moving to 3 photon, and we're going to intensity cubed. So you can think every time I need this, I need another laser pulse, I need higher power. But again, we want to come back to our concept of entanglement. Because entanglement, basically, you've already rear-ended everything. All that matters is just the number of cars going through. It's in this state where it's 2 photons at the same time while appearing as 1 photon. So because of this, the hope is that we could take 2 photon absorption like this and make it a linear process. So if on this graph, if it was a 2 photon process, it goes something like this. Now, this is something we've been working on in our lab. Actually, some of the first measurements of what we call entangled 2 photon absorption, there's some jargon, came about from Jeff Kimball here, and then Ted Goodson and a lot of others innovated over the next few years, and now it's become quite a popular field. But it's an interesting field here, and this is why I'm going to show a little bit of data with it. Why I say it's interesting is because you would think we'd understand how the entanglement works. I can make the entangled photons, right? We should understand how they interact with things. But we're at a very interesting point with entangled photon spectroscopy because neither theory or experiment right now can really agree on anything. But the test case we're all trying to do is this 2 photon process in the hopes that we could eventually move to a much smaller laser. We can bring this imaging to hospitals and what goes with it. So it's quite interesting, but the issue is, as you can see here, these gray lines, this is a linear slope. This would be if things worked according to theory. What we actually measure is this orange line. And actually, after doing a lot of measurements, we figured out this orange line isn't even fluorescence. It has nothing to do with entanglement. So this field right now, I want to bring this up because it shows you, you may think, okay, quantum mechanics has evolved. It's standard. We use it in everything. But here's the disagreement in my field right now about what entangled 2 photon absorption is. We're talking about, basically 10 orders of magnitude of different, I don't want to say guesses, 10 orders of magnitude of different theory, experiments, and no one can get to the bottom of this. And the reason is because we're now not just having light interact with an electron. We're having an entangled state interact with an electron. And with that, we're at a point where, theory is trying to catch up. Experiments are very hard. To give you an idea, I told you we were doing single photons. Well, I'll talk in a little bit about to make these practical, we make more than that. But basically the relationship you can use, and I apologize, I'm stealing this analogy from someone that I forgot their name, is that the type of measurements my students do, it's like trying to be, say, on top of the Angeles Crest Mountains and see a candle in Colorado. That's the amount of flux we're dealing with. It's insane how many photons are around you. In this room right now, there's something on the order of 10 to the 16th or so, I think 10 to the 16th photons. The sun's like 10 to the 18th photons that are all around you, right? That's an insane number. But we need to get that to 1. So you can imagine the challenge here, and that's where a lot comes with, but it's also the concept of we have no idea what's going on in the excited state. So we've also been looking at other interesting ideas. And we're saying, okay, maybe having this as just 2 photons at the same time What if we have one entangled photon interact with a state? This is like an absorption, like I said. This is like, say we have blue paper and we're shining white light at it. You absorb, well, you're seeing the blue, you absorb everything else. But what we're now looking at is saying, okay, well, what if we try to entangle our initial state that we're exciting? For everyone here, you know, we're trying to entangle an S0 to S1, basically spin. And then we have another, entangled photon come in, and then we're trying to see, okay, if that state's entangled with one photon, will it work with the other one to have a strong interaction? And we thought we were there. We got this data a couple months ago, but again, we aren't quite so sure now that we did control experiments. But you can see where kind of the newness, this is why a lot of people call, you know, quantum information sciences, quantum computing, a lot of these things that use entanglement, kind of quantum 2.0. Because we have a set of quantum mechanics which works insanely, you know, we can calculate things for hydrogen atoms like 10 decimal places and it's accurate. But we now have this new problem where we bring in entanglement and these other things, and all of a sudden we're back at square one. You know, sometimes even I think to myself, okay, what is actually happening in this molecule when it's entangled? And I don't have any idea, but we're working on it, right? That's what we do fun science for. So we're slowly working through this though, but there's another thing that we can do. In one way, that's kind of talking about, okay, I just want to get rid of big expensive lasers and bring these more complex spectroscopies to the world. The other thing though is kind of like my last example, because you can ask yourself, okay, is entanglement fundamental to things like bonding? Is entanglement fundamental to what we call many-body interactions? When you have a lot of electrons interacting, a lot of vibrational modes interacting, are these just quantum states, like I said, you know, the indistinguishable or the distinguishable, we're just adding them up? Or fundamentally, are we working with entanglement? So the idea of where we're now moving with entangled photon spectroscopy is, okay, once we can actually figure out, okay, well, this is how it works, we've got it, we trust it, which we recently, I have to get a lot of credits from my graduate students for working hard on this. You know, they basically worked in the lab, they would change setups every month, every week sometimes, but we finally have our system built where we really trust it and we can look for these kind of results. This is how we figured out our one result was false, you know. Sometimes you work for years, your result is false, it's devastating, but that's science. We have to take slow steps to get where we need to be. You have to be careful. But what we're looking for now is, okay, saying we have this good spectrometer, is there actually entanglement in there? Because if there is, it'll intersect strongly with our states, and we can see that modulation on that dip I showed you. So, what I'm talking about here is there are concepts, theoretically, that say this right here is a picture of a quantum mechanical calculation of the electron density of this coupled molecular pair. You see it's evolving in time, but you see the thing is we don't draw it as a point. It's just some density. It's a probability. This right here is a very mature quantum mechanical calculation called density functional theory, or time-dependent density functional theory that leads to this. But the question is okay, if these electrons are in this probability distribution, are they separable? Are they a superposition? Or if we get a lot of them together, is there some underlying entanglement that could lead to new phenomena? You can especially think of this, you know, once we start bringing together lots of different molecules or lots of different materials. This one right here is actually basically slowly building up to what you call the photosynthesis molecule, which works similarly to your eye. And in there, we already know we have something called quantum coherence, which means when we have light hit it, all the thing is working at the same time. All the electrons are moving together. And that's essential for these things like photosynthesis, and it's theorized even for sight. It's actually even, there's some very interesting things in the field of what we call quantum biology. Debated, but it's interesting. But the question is, okay, if this is in this natural coherence, is it coherence or is it an entangled state? And the thing about entangled spectroscopy, one of the big reasons we're developing it, is you need entangled photons in order to determine that entangled state's impact. You can infer it from classical measurements, but it's best to measure like with like. So, a little bit more here. I told you I was going to keep getting more complex. Here's a diagram that's getting more slowly accurate to what we actually have in the lab. Slowly building up components here. We still have our entangled photon source itself. Then in here we have a bunch of mirrors and things and all these different detection electronics in order to try to measure this dip. Well, because of our setup, that dip looks a little bit different. But I want you to keep the same thing in mind because I know I just threw up a bunch of squiggly lines and that kind of gets I don't know. It makes a lot of our lines turn off. I actually had a colleague back in my PhD who tried to title his thesis, My Observation of Squiggly Lines, but unfortunately someone at the university caught it at the last moment, but I wish you could have published it. Because this is right here is what we look at. But you can see this isn't a dip per se, it's a different variant of this measurement, but we do see kind of a dip pattern. Now it just goes up and down, and we have these oscillations going on. So these oscillations, when we're doing this entangled spectroscopy, are what are informing us. Is this a classical state? Is it excited? Is there entanglement inherent to the system? What's going on with it? And so these are the types of measurements we're using to explore the systems I talked about. Okay, so that's kind of the basis of what we're doing. You know, I've showed you some results, and like I said, I want to be honest, a lot of our results, we got very excited, they're false, but that's how you keep going. But now I want to show you kind of the vision and what I was awarded the K&I Wheatley Fellowship for. And like I said, that's to slowly take these very advanced techniques and make them smaller and smaller, because we do know that part works. The entanglement, how it interacts with the universe, well, there's a lot of philosophy, science, and theory to be done there. But we know we can shrink lasers. So the idea here is I told you, okay, we already went from using a pulsed laser into what is basically the equivalent of this laser diode. Now we want to go one step further. And we want to say, okay, can we take it from this to this to this? Can we take this complex setup that otherwise you need a PhD to run and shrink it down to a chip so that we can integrate it, you know, with deployables, with medical technologies, with whatever you want to go with it? The idea is to slowly get here, and this is where our concept of nanofabrication comes into place. Nanofabrication is describing basically taking these elements, then we get here, and then making them even smaller. So here, for example, is one of our chips that we have. Now right now, eventually it's going to be a complete spectrometer. Right now we're just producing entanglement, but you can see this is about a centimeter by a few millimeters size, and it's slowly replacing our entire setup. Now, when we get here, it looks different, but it's actually a simplification of the more complex instrument I just showed you. In other words, you can see, okay, we're going to make our entangled photons, then we have kind of what looks like a four-way intersection, right? Then we have some time delay, then we have another four-way intersection, and our sample would be in that intersection. So with this, we're basically taking that whole measurement, looking at the data I was showing you, trying to power, let's say, a 2-photon microscope, and shrinking it down. Another way to say it is, again, you know, what we're trying to do here is by using entanglement, we're just trying to squeeze all of these cars onto this small chip and have all of your friends there to help us observe them. So, just to show you again a little bit of cool data, because I'm very proud of this. As I told you, one of our big issues we face is I told you that doing single photon spectroscopy is looking like looking at a candle in basically Colorado. It takes insane amounts of patience and time and very, very careful things. That's not realistic for the real world, right? When we do single photons, it can take basically 3 to 4 hours to get like a single good data point. So we need to increase the number of photons we have. But there's a trick to it, right? Because I told you classical light is when we just bring a bunch of photons together. So we don't want to make classical light, we want to be able to make a large amount of entanglement. So the way we do that is basically by spreading things, as you could say, across the rainbow. We make a bunch of entangled pairs that each one has a different color. And by combining these, we can actually make a source here. I was giving you references as, you know, the number of photons in this room. We're going from, you know, maybe like 10 to the first, 10 to the second photons to around 10 to the 13th photons. So we're now getting, this picture right here was actually taken with a cell phone camera. You can walk into my lab, we can put a note card in there, and you can see entangled photons. Now, I mean, it's cool. It's very cool to me. I remember the first time when we got our first chips made, we searched for probably a month, and then finally one day someone just put a card in front of it. We're like, oh my gosh, it's been there all along. Weirdness of entanglement, don't ask me. So, but it's very cool. You can see these by eyes. So now I've moved that candle basically from Colorado to say, you know, okay, maybe a couple miles away from you. Now we're getting to the range where we can start doing this spectroscopy, because these entangled states are fragile. So if you want to do it, you not only need a lot of them, but you need the ability to lose a lot. It's almost like doing error correction, right? You do error correction, you do things a lot of times, and then you match them and make sure it works. We're just trying to multiplex our system. So to do that, though, we need a lot of elements, and this is where my collaboration with Alireza comes in, and this nice continuity we have with this award. These right here are just some pictures of us making our first chips that slowly go into it. Here are some input and output fibers. Very delicate things. But our main idea here is the way we're making these entangled spectroscopy basically feasible on a chip is we're basically, like I said, taking a lot of different what we call nonlinear elements. You could think, this layer right here makes blue, this makes green, this makes orange, this makes red, et cetera, et cetera, et cetera. And from that, we're able to take, again, a laser pointer, something that we can theoretically, you can integrate them on chips, even though getting it all together could be a bit of a mess. That's a project that, me and Alireza are dreaming about right now. But you could theoretically, on chip, have an entire contained nonlinear spectrometer that gives you better pictures of this roadmap. So you can do fun things like this. This right here is what a 2-photon absorption microscope looks like. I don't know, probably about $300,000. I don't know I've never bought one myself. But it's something that looks like this, and there's issues with it, like I said. If you want those images, you need powerful images. Betty does what I think is the coolest science, and that Betty basically, well, the poor flies, but you remove part of a fly's head, and then she basically measures how their neurons fire as she feeds them smells to try to figure out, okay, how does your brain process the smell? But of course, you can imagine, A, the head's open, B, we're also shining a very powerful laser on the brain. 2 and 2 don't go together the best. Now, of course, these scientists who are wizards have made it work very well, but there are some cases where we need lower power. But the more exciting thing is you can imagine, if you wanted to study something here, you got to pin it to the microscope. So one day these sources, one is doing knowledge spectroscopy, the other is doing things like I just told you, this 2-photon microscopy, where theoretically our final chip plus, the battery is going to be bigger than the chip. You can make this small module. Right now, an entangled setup, for us, it costs in the lab about $10,000 to put together. That's without any economy of scale buying complete scientific parts. But compared to our other lasers, which are in the 100,000 range, you can imagine how this can slowly get to the cost of scale we get with microchips. So, kind of my dream here, what I kind of want to end on is that, entanglement is a fun thing. It's leading to a lot of new technologies. We have no idea of which ones are going to dominate our life, what's going to be the new cell phone, what's going to be the next one. But it brings a new degree of mystery to quantum mechanics in which scientists are exploring for cool technologies. And me in particular, well, I'm trying to take it so that even my little Chinese child brain can go and measure this entire roadmap at once, basically instantaneously, so I can understand the full system. But I want to do that with something smaller than this. I don't even want a laser. Well, first we'll have to get here. But I want to get all the way down to including this so that we can have advanced technologies, these advanced measurements, things like measuring kinetic rates for biological reactions. You could think of measuring pollution for LiDAR, for all these different applications. We want to get nonlinear spectroscopy there. So with that, I kind of want to wrap up here and conclude. And of course, I want to thank several people again. So much thanks to the Wheatley family. It's been wonderful meeting you and chatting earlier and allowing the science that you do. I also want to thank the Rosen Bioengineering Center, which first funded my crazy idea with Betty and her continued patience as it takes us years to try one more step. And I also want to thank the United States Department of Energy, who funded a lot of this work that I told you about. But I want to leave on my conclusions here. One, there's a lot of interesting applications when you start to use entangled photons for spectrometers instead of stay a component of an information system or computing system. When you start doing spectroscopy, it's a very open and you could say largely unexplored field. The other one is the key, and this is what we are funded for by the K&I Wheatley Fellowship. You can't do this unless things are bright. You can't measure something unless you got a lot of data. You have to be able to acquire that quick for it to be practical, and that's one of the things that we're working on hard in our lab, and we've achieved it. Now we're working on making more custom sources and getting on chip. The other one is, this is a fun one. I think, as me and Alireza were talking earlier, slowly but surely, he has a technology that uses classical light but can do similar things. We're kind of going at it from the same approach to see, which one can work, but we're slowly moving towards an age where these spectroscopies, these laser spectroscopies that have been developed for decades in laboratories, dozens, thousands of PhD lifetimes, we're slowly getting to the ability where we can bring these into systems. We can go from just an X-ray image or a blood measurement image to an actual decomposition of what's in your blood. This more and more information, we're slowly going towards this nexus. I also want to say, we have published papers on this, but I wanted to put up the preprints just in case you aren't in the scientific audience and you don't have access to these journals. So this first paper right here, if you're interested, this is a summary of the field of entangled photon spectroscopy we wrote, kind of a review of what it is and where it could potentially go. If you're interested in bright sources, here's another paper. And then right here is where we first started to do some of our first experimental things, which ended up, like I said, after many months of no result. But from no results, you always learn something new. So better things will continue to come. And with that, I just want to thank you all so much for your attention. So we'll now switch over. It's an open Q&A session. If you have any questions, feel free to come up to the microphone. My student is also going to list some questions that may have came up on the YouTube live feed of this. But I'm very happy to answer anything you may have. And if not, I just hope that you only remember me in cars and not toilet paper when you leave. But think of quantum mechanics. Bryce, were there any online?
Unfortunately not.
Okay, no problem. So if you aren't comfortable coming up to the microphone, I'm going to sit around on stage for a little bit. Feel free to come up and chat with me. I'd be more than happy to. Again, thank you all so much for your time and for coming.